In 1950, physicist Enrico Fermi posed a question that would become one of the most intriguing puzzles in science. While having lunch with colleagues, he suddenly asked, "Where is everybody?" Enrico Fermi was a brilliant Italian American physicist who made groundbreaking contributions to nuclear physics and quantum theory. His simple question would spark decades of scientific debate and speculation. To understand why Fermi's question is so profound, we need to consider the sheer scale of our universe. Our galaxy alone contains hundreds of billions of stars, and many of these stars have planets orbiting them. When we look beyond our own galaxy, the numbers become even more staggering. There are an estimated 2 trillion galaxies in the observable universe, each containing billions or trillions of stars. Given these astronomical numbers, it seems statistically inevitable that life should have emerged elsewhere in the universe. Some of these civilizations might even be millions or billions of years more advanced than us. This brings us to the heart of the Fermi paradox. If the universe is so vast and old, and if life is likely to emerge on many worlds, then where are all the aliens? Why haven't we detected any signs of extraterrestrial civilizations? This contradiction between expectation and reality is what makes the Fermi paradox so compelling. It forces us to question our assumptions about life, intelligence, and our place in the cosmos. Are we truly alone, or are we simply not looking in the right places? The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicating extraterrestrial civilizations in our Milky Way galaxy. This equation breaks down the complex question of alien life into 7 measurable factors, each representing a crucial step in the development of a communicating civilization. Let's examine each variable in the equation. The first factor, R star, represents the rate of star formation in our galaxy. Approximately 1 to 3 new stars are born each year. The fraction of stars with planets Fp has been revolutionized by recent discoveries. We now know that most stars have planetary systems, with estimates ranging from 20 to 50%. The number of habitable planets per system, NE, focuses on worlds in the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist. The remaining variables become increasingly uncertain. The fraction where life develops, FL, is based on only one example, Earth. We simply don't know how common or rare the emergence of life truly is. The final variable, L, represents how long civilizations remain detectable. This could range from decades to millions of years, creating enormous uncertainty in our final estimate. When we plug different estimates into the Drake equation, we get wildly different results. Optimistic estimates suggest thousands of civilizations, while pessimistic ones suggest we might be alone. This enormous range of possibilities is precisely what makes the Fermi paradox so compelling. The Drake equation suggests life should be common, yet we see no evidence of it. The equation reveals that our estimates depend heavily on factors we barely understand. Each variable represents a filter that life must pass through, and the uncertainty in these values keeps the Fermi paradox alive. The Great Filter is one of the most compelling explanations for the Fermi paradox. This concept suggests there exists a critical barrier that prevents most life from advancing to become a spacefaring civilization. The Great Filter diagram shows how civilizations attempt to progress through various evolutionary stages. Most species are stopped by this critical barrier, with only rare exceptions managing to pass through. The Great Filter could be located at different points in evolutionary history. If the filter is behind us, it means we've already overcome the most difficult hurdle. But if it's ahead of us, our future survival may be in jeopardy. One potential Great Filter could be abiogenesis, the emergence of life from non-living matter. The Miller-Urey experiment demonstrated that organic compounds can form under early Earth conditions, but the jump to actual living organisms remains mysterious. Another potential filter is the evolution of complex life. Earth's history shows that simple life existed for billions of years before complex organisms emerged. The development of multicellular life, intelligence, and technology each represent significant evolutionary hurdles. If the Great Filter lies ahead of us, it could take the form of catastrophic events that destroy advanced civilizations. Asteroid impacts, like the one that killed the dinosaurs, demonstrate how cosmic events can reset evolutionary progress. Perhaps most concerning is the possibility that civilizations destroy themselves through war, environmental collapse, or other self inflicted catastrophes. The desolate landscapes left behind would offer no trace of what once was. The Great Filter concept forces us to confront a sobering question. Are we incredibly lucky survivors of an evolutionary gauntlet, or are we approaching our own extinction event? Understanding where this filter lies is crucial for humanity's long term survival. The Fermi paradox has puzzled scientists for decades. If the universe should be teeming with life, where is everybody? Several compelling explanations attempt to resolve this mystery. The first major explanation suggests that life itself, especially intelligent life, is extraordinarily rare. Perhaps Earth's conditions are far more unique than we realize. Earth's climate system demonstrates the delicate balance required for life. Small changes can trigger feedback loops that make a planet uninhabitable, as shown in this climate model. A second explanation is far more sobering. Civilizations may routinely destroy themselves before achieving interstellar travel. This could happen through nuclear war, environmental collapse, or other catastrophic events. The threat of nuclear destruction has loomed over humanity since the 1940s. Many civilizations might not survive this critical period in their technological development. Even if civilizations survive their early technological phase, they face enormous barriers to interstellar travel. The distances are vast, the energy requirements immense, and the technical challenges may be insurmountable. The nearest star system, Alpha Centauri, is over 4 light years away. With current technology, it would take tens of thousands of years to reach it. The energy requirements for faster travel may be prohibitive for most civilizations. Finally, advanced civilizations might simply not last long enough to be detectable. They may rise and fall within brief windows of time, missing each other across the vast timeline of cosmic history. These explanations suggest that the silence we observe might be the norm rather than the exception. Whether due to rarity, self-destruction, technical barriers, or brief lifespans, the universe may be far lonelier than we hoped. Perhaps the answer to the Fermi paradox isn't that alien life doesn't exist, but rather that we're approaching the search in the wrong way, or that extraterrestrial civilizations are deliberately avoiding contact with us. One possibility is that we're simply not listening correctly. Our search methods may be fundamentally flawed. We might be looking for the wrong types of signals, using outdated technology, or searching in the wrong places entirely. The zoo hypothesis presents a fascinating alternative explanation. This theory suggests that advanced alien civilizations are aware of Earth and humanity, but they deliberately avoid contact with us, much like how we observe animals in a zoo without interfering with their natural behavior. An even more sobering explanation is the dark forest theory. This concept suggests that the universe is like a dark forest where every civilization is a hunter. Any civilization that reveals its location risks being destroyed by others, so the safest strategy is to remain completely silent and hidden. Some advanced civilizations might have transcended physical reality entirely, moving into virtual worlds or higher dimensions that we cannot detect. Others might have developed technologies so sophisticated that they appear indistinguishable from natural phenomena, making them invisible to our current detection methods. These theories suggest that the silence we observe might not indicate the absence of extraterrestrial life, but rather reflect our limitations in detection methods or the deliberate choices of advanced civilizations to remain hidden for their own survival and development. The search for life beyond Earth has been revolutionized by recent exoplanet discoveries. These findings have fundamentally changed our understanding of how common planets are in the universe. Since the first exoplanet discovery in 1995, we have confirmed over 5,000 planets orbiting other stars. Remarkably, about 1 in 4 stars has Earth-sized rocky planets in their habitable zones. But finding planets is only the first step. Scientists are now searching for biosignatures, specific chemicals in planetary atmospheres that could indicate the presence of life. These include water, oxygen, methane, and carbon dioxide. We detect these biosignatures using a technique called spectroscopy. When starlight passes through a planet's atmosphere, different gases absorb specific wavelengths of light, creating a unique fingerprint we can analyze. The James Space Telescope has revolutionized our ability to study exoplanet atmospheres. Its unprecedented sensitivity allows us to detect and analyze the chemical composition of distant worlds with remarkable precision. Here we see real data from the James Webb Space Telescope showing the atmospheric composition of an exoplanet. The graph reveals the presence of water vapor, detected by analyzing how different wavelengths of light are absorbed. This comprehensive analysis shows data from multiple instruments aboard the James Webb Space Telescope, all studying the same exoplanet. Each instrument provides different pieces of the atmospheric puzzle, revealing water, carbon dioxide, and other molecules. This detailed spectrum shows the detection of multiple atmospheric components, including water, sulfur dioxide, and carbon monoxide. While not definitive proof of life, these detections demonstrate our growing capability to analyze alien atmospheres. These discoveries represent just the beginning. With more sensitive instruments planned and artificial intelligence helping to analyze complex atmospheric data, we may detect definitive signs of life on other worlds within the coming decades. The search for extraterrestrial intelligence, known as SETI, represents humanity's most systematic effort to detect signs of alien technology. For decades, radio telescopes have been scanning the cosmos, listening for artificial signals that could indicate the presence of advanced civilizations. Radio telescopes like those used by SETI point toward different regions of space, collecting electromagnetic radiation. These sensitive instruments can detect incredibly weak signals from vast distances across the galaxy. When radio telescopes detect signals, they are analyzed for patterns that might indicate artificial origin. Scientists look for narrowband signals, repeating patterns, or other characteristics that natural cosmic phenomena typically don't produce. Technosignatures are any measurable effects that provide evidence of past or present technology. Unlike biosignatures, which indicate life itself, technosignatures specifically point to the presence of advanced, technology-using civilizations. Scientists search for various types of technosignatures. These include radio transmissions, optical laser pulses, and even massive engineering projects like Dyson spheres that could block starlight in detectable patterns. However, there's a fundamental problem with our search methods. We tend to look for technosignatures based on our own technological development and assumptions about how civilizations should grow and communicate. We assume that alien civilizations will follow a similar technological progression to ours, from radio communications to digital technology to space exploration. This assumption may cause us to miss entirely different approaches to technology. Alien civilizations might develop completely different technologies that we haven't even imagined. They could use quantum communication, biological computing, or energy sources we don't understand. Our search methods might be completely inadequate for detecting such technologies. This creates a fundamental detection challenge. Advanced alien civilizations might be using technologies so different from ours that they're essentially invisible to our current search methods. We may be looking for the wrong signals in the wrong places, using the wrong assumptions. Despite these challenges, SETI continues to expand its search methods and technologies. Scientists are developing new approaches to detect a wider range of possible technosignatures, acknowledging that the universe may hold forms of intelligence and technology far beyond our current imagination. The search for extraterrestrial life has evolved into a complex, multifaceted endeavor that requires expertise from many different scientific disciplines working together. One critical insight emerging from this interdisciplinary approach is the growing recognition that sustainability may be the key to long-term civilization survival and detectability. Scientists are also working to refine the parameters of the Drake equation, using new data from exoplanet discoveries and improved understanding of planetary formation to better estimate the probability of finding extraterrestrial civilizations. Future space telescopes, like the planned Habitable Worlds Observatory, represent the next generation of tools that will search for chemical signs of life on other planets, potentially providing the breakthrough we need. The comprehensive approach to solving the Fermi paradox combines all these elements. interdisciplinary collaboration, sustainability considerations, refined mathematical models, and advanced technology. As we continue this search, the integration of sustainability science, advanced technology, and interdisciplinary thinking may finally provide the answers to one of humanity's most profound questions. Are we alone in the universe?